This is not a robot.
This is a learner. And the real secret to Boston Dynamics isn't the perfect jump, it's the fall. We've all seen the videos. Atlas doing parkour, Spot navigating a construction site. They look slick, polished, perfect. And our first assumption is that they are programmed, like a video game character. We assume some brilliant engineer sat down and wrote, if obstacle is 0.5 meters high, then execute jump routine 4B. We are completely, fundamentally wrong. That single polished video that goes viral is the result of millions of failures. The truth is, these machines are thinking, but not in the way a human thinks. They are learning. By the end of this analysis, you will understand the 3 core AI principles that separate Boston Dynamics from everyone else. And the third one, that's the real game changer. This is Boston Dynamics Decoding.
To understand where Boston Dynamics is going, you have to understand where we came from. This is the old way. This is a static, programmed robot. It's incredibly good at one thing, moving from point A to point B, in an environment that never changes. If the conveyor belt is 1 millimeter off, the entire line fails. Its world is predictable and controlled.
This is the new way. This is dynamic control.
The primary goal of the Atlas robot isn't to follow a specific path. The primary goal is to not fall over. It's a system of constant, real-time balance correction. It's an entire philosophy built around surviving the real, chaotic world. Think about it. When you walk, you aren't programming your feet. You aren't thinking, left foot 30 centimeters forward, right foot 31 centimeters forward. You are simply thinking, I want to go to the kitchen. Your brain and inner ear handle the billions of micro-corrections to keep you upright, even if you step on a Lego. That is the base layer of a Boston Dynamics robot. It's a physical platform designed to be inherently stable, to fight chaos, to survive. But this incredibly sophisticated body is useless without a brain to tell it where to go and what to do when it gets there. And this is where the real secret lies. Because Boston Dynamics doesn't program the brain, they grow it. What you are looking at is the most important part of the Boston Dynamics process. It's not a lab, it's a simulation. This is the core concept of reinforcement learning, or RL. And it's actually simple, like teaching a dog to sit. You don't program its muscles, you just give it a reward. A treat when it does the right thing. And over time, it learns that sitting equals reward. Boston Dynamics does the exact same thing. In the simulation, they don't tell the robot how to jump the wall. They simply give it a reward, a positive score for any action that gets it closer to the goal. And they give it a penalty, a negative score, when it falls or hits the wall. Now imagine doing that 1 million times per hour. The AI is literally teaching itself. It's building a memory of what works and what doesn't. It learns that this specific angle of lean leads to a fall, but that specific leg placement leads to a successful step. This is why the fall is more important than the jump. Each failure is just a piece of data, a penalty that tells the AI, don't do that again. So before the physical Atlas robot is ever switched on, its brain, its digital twin, has already lived thousands of lifetimes. It has failed more times in a single day than a human will in their entire life. It has already learned how to walk, how to run, how to jump, and crucially, how to get back up when it falls. This simulation-first approach is their first major secret. And by the way, if you are getting value from this analysis and want more deep dives into the tech that is actually shaping our future, take a second and hit that subscribe button. We're just getting started here. But there's a problem. A simulation is clean. It's just math. The real world is messy. It's full of friction, wind, loose gravel, and people who get in the way. Knowing how to walk is useless if you don't know where to walk. This is what Atlas actually sees. It's a constant 3D scan of its environment. This is perception AI, or computer vision, and it's the second part of the brain. The robot doesn't see a wooden box. It perceives an obstacle, 0.5 meters high, 1.0 meters wide, stable. It doesn't see a gap. It perceives a gap, 1.2 meters, jump required. This is the critical fusion. The two parts of the brain work together. When Atlas approaches this parkour course, its perception AI, its eyes, scans the world. It identifies the ramp, the gap, and the landing platform. It feeds this data, gap 1.2 meters, to its reinforcement learning model, its brain. The brain then queries its millions of simulation-trained memories and says, I've seen this before. A 1.2 meter gap requires jump routine 74G, which I learned through 50,000 failed attempts. It then calculates the precise power, angle, and timing needed, and it executes the jump. This is why it's not programmed, it's reacting. It's taking in new live data, perception, and applying its vast library of learned experiences, reinforcement learning, to solve the problem. It's the synthesis of seeing and doing. But this leads to the final and most important question. If the simulations are so good, why does Boston Dynamics spend so much time bullying their robot?
This looks like bullying. It looks cruel. It is, in fact, the final exam. This is the chaos principle. The AI was trained on perfect data, the clean math of the simulation. It was then refined on imperfect data, the basic physics of the real-world lab. Now it must be tested against chaos data, the truly unpredictable, unprogrammable, unexpected nature of reality.
The hockey stick is not in the simulation. The thrown box is not in the code. The engineer who suddenly walks in front of Atlas is the one variable it could never have been programmed for. This is the test. Does the robot panic and freeze? Does it default to a useless error message? Or does its dynamic control system take over? Does its perception AI see the unexpected obstacle? Does its reinforcement learning brain access a similar memory of falling and apply it to this new situation? When the robot stumbles, adapts, and stays upright, that is the moment the test is passed. They are literally building anti-fragile machines. They are training the AI to expect the unexpected. This is what makes a robot robust enough for a construction site, a disaster zone, or a factory floor, and not just a sterile lab. It proves the learning was successful.
So, how does an Atlas robot really think? It doesn't, not like us. This is the most misunderstood part of Boston Dynamics. This AI doesn't wonder, it doesn't fear, it doesn't get bored, it doesn't dream. It solves. It is a hyper-specialized physical problem-solving engine. It was grown in a virtual world, trained on millions of failures, and tested against chaos, all to achieve one goal: execute a physical task in the real world no matter what. The real analysis, the final hard truth: Boston Dynamics isn't just building robots. They are building an engine that learns from failure, an engine that can be pointed at any problem: robotics, logistics, medicine, finance, and told, fail 1,000,000 times a second until you find a solution. And that is a far more powerful and frankly terrifying concept than any parkour video.
So, what's your take? Is this the inevitable future of automation, or is it a step too far? Drop your analysis in the comments below. I want to know what you think. And this learning engine is already moving beyond robots into AI systems that will change everything.